Hello and welcome everyone to a blend of analysis, one product, every discipline. My name is Robert Warren. I'm a simulation specialist here at GoEngineer, and I'm located in Cleveland, Ohio. Today we're going to talk about a product development, and that product that we're going to be looking at is the GoBlend blender. This kitchen appliance boasts of being fully designed in SOLIDWORKS and 3D Experience. This blender has been scientifically optimized for its structural integrity, electronic thermal management, manufacturability, and of course its capability to blend a killer smoothie. Touchscreen controls and a smart Wi-Fi connection round out its expected capabilities. Let's take a look at how this blender went from concept to optimal design. Before we begin, one additional requirement: marketing wants the blender base to represent the company logo. So where we're going to go in this presentation is just talk about the concept, how we got to the model that we're going to be looking at. We'll talk about structural analysis, fluid analysis, manufacturability, and electromagnetics. So let's talk about the blender, the 3D model, and the journey of how we developed this design so far. So we did a lot of research, right? This is where anybody would start. We wanted to understand, what others are doing, what's on the market now. So we investigated. We wanted to understand all the components necessary to create the product. We put pencil to paper, literally. We drew out the design, the different ideas that we had, and we took those sketches and we turned those sketches into a solid model. Now, along the way, there were some pitfalls, right? Manufacturability, for one. I talked to our plastics engineer, Bill Roos. He indicated, hey, we can't injection mold this. That corner is pretty much impossible. So, did a lot of redrafts just with the initial thought process of the solid model. During the design process, we used structural analysis, computational fluid dynamics, manufacturing analysis, and electromagnetics to help develop the blender to what we see here. Let's look at the picture handle. The handle looks stylish, and our intuition indicates it can withstand a large load, but we do not want to move up to a prototype before we confirm the handle can withstand 25 pounds of product in the picture. It's way more than what we would normally expect. We know we need to stay below a stress of 1200 psi to keep a factor of safety of 2 or better. Let's see how the handle performs. Inside of SOLIDWORKS, we can save the model to 3D Experience platform. On the right-hand side of the screen, we have a direct access to save the model to the platform, even choosing specific bookmark to place the model. Once the model is uploaded, we can select the model from the bookmark and launch our structural analysis tool. First step to setting up the model is to use the finite element representation, a FEMREP. We're using an automated FEMREP to generate the solid sections and initial mesh. Choosing the solid sections tells the software what parts we want to use in the analysis. Renaming the solid section is a good rule of thumb, and we can specify the material to use right in this property manager. So we can see we're choosing a plastic. It's going to be a polycarbonate, and we can see the simulation data associated with that component. We're going to do the same thing for the next solid section. We're going to rename it. That name is handle, and we're going to pick a material, and in this case is going to be a nylon 610, and we can see the material properties associated with it as well. The mesh was created during the auto FEMREP stage, but we want to refine the mesh further. We can edit the mesh for both solid sections. So by editing these, we can go in and we can refine the mesh size. We can also tell it no sag, which means it's going to map the geometry perfectly. And we can see that refinement on the handle itself. From here, we're going to add some connections, and in this case, we're going to add a tie. Now, in reality, this handle is a kind of a press fit or a friction fit. However, to best mimic what's happening in the model, we're really pushing down, so it's going to always be in contact. We're just going to use a tie between these two components, basically bonding or holding them together inelastically. We're going to go ahead and save the study. From there, we're going to start our static scenario app. We can see we're going to name the simulation. So we'll give it a name here. So pitcher handle. And we chose the finite element analysis model that we just created previously. We're also going to go in and add a procedure. So we're going to add a static step. And we're going to choose our boundary conditions. So we will assign a clamp to the upper portion of the handle, basically saying, okay, this is where it's going to be held, maybe with our thumb and our forefinger. We're also going to add a roller slider to the back face of the handle. This is where it would be maybe in contact with the palm and the other fingers in our hand. So we're going to allow it to kind of move right and left there. We're going to assign our force to the bottom face. And again, this is going to be 25 pounds, probably a lot more than this pitcher would ever see in real life with regards to a smoothie. From there, we're going to go ahead and solve the analysis. So we can bring up the solve property window, and we have a lot of different options. We can solve locally. We can also solve on the cloud. We're going to do a local interaction here. With this specific version of the software, we get 4 cores embedded for free, and we'll go ahead and start that solve. Once the solve is complete, we can take a look at the results. Now we can see stress on the handle. This is the first result, and you notice that we have 1 increment. That's because this was a static study. So we're looking at the end result. And we can see our stress, the maximum stress is 885 psi. Remember, we had to stay within 1200 psi. So we're looking pretty good with respect to those results. We can actually animate this. Notice that this is exaggerated. The pitcher is not deflecting this much, but it gives us a feel for how the pitcher is going to deform, how it's going to move. And we're seeing that holding that handle, right, we're expecting that deflection in the direction that we have there. So that makes sense to me with respect to the results. We can go ahead and change the deformation scale as well. So we can edit that plot, and we can shake this back to a deformation scale of 1, basically a 1-to-1. So this is a true deformation in the model. We can also look at different things within this plot. So anywhere I move my cursor, we have a probe tool, so we can give us the value of stress in those areas. The other thing with respect to this is we can look at the displacement. So the displacement allows us to kind of understand how much is this moving, and really 0.4 millimeters, so half a millimeter at that maximum distance really isn't a lot. We can also go in and do plot sectioning. So we can pick different planes to section through, and with that we can actually even change to the stress plot with the section still on and understand, what is the stress on the back of the handle. Maybe we'll move this section a little bit to understand what is the stress right through that fillet. So if I pick on my plot sectioning again, we can move that section and we can understand how far the stress penetrates through the arm itself. So a lot of good feedback with respect to the outputs. From there, what I want to do is go back into 3D Experience, and I want to make sure that I have all of my components associated in that bookmark that we talked about earlier. So I'm going to pick up the relations of this model, and I'm going to pick up the results and the finite element model, drag those into the window, and we now have access to those results again. When we go back to the picture linear for the GoBlend structural in that bookmark, we can always get back to our study very quickly. So with regards to structural, I did a couple more analyses. One was a drop test, and I used SOLIDWORKS Simulation Professional to perform this. Now the drop test is on the picture itself and the blade assembly. We did not include the handle on this one. So moving back into SOLIDWORKS Simulation, I'm going to go ahead and start a new study, and I'm going to choose drop test. Now this is a nonlinear caveat of the Simulation Professional module. I have stainless steel assigned to the blade and the shaft for the blade, and then we have the polycarbonate assigned for the picture itself. We have a fairly refined mesh on the model, so not too coarse but not too fine, so it looks pretty good. And we're going to look at the setup. So I picked the right plane as my direction of gravity. I also told the software that it's going to be 36 inches above the ground, so we're giving it a drop height. However, we could give it a velocity at impact as well. And I'm specifying that the target is rigid, however, it could be flexible, could have some give to it. And then I'm also going to tell the software how many seconds, microseconds, past impact we want to see the results. Now the next step is really to run the study and then take a look at those results. So I already ran the study. Let's go ahead and jump into the results. So here we can see, we can animate the results. We can see it kind of come in contact with that ground plane. We can see the stress developing as it comes into contact. I'm going to go ahead and edit this, and I'm going to make it an automatic scale. So this is exaggerated again, but it's really showing how that deformation would be occurring on an exaggerated scale. So we can actually see almost a buckling on that lid or on the edge where the lid would connect. We can look at displacement, we can look at strain, we can also look at the response. So there we saw the response graph of the force of this impacting. Now, again, this is a nonlinear caveat. It is limited, right? We can't include the fluid that's associated with being inside the picture. We do not have the lid. We do not have the handle just because of some contact considerations. We'll see later in another structural analysis we can include those. So another structural analysis was the press of the lid onto the picture itself. Now we have the gasket seal, and I originally put 5 seals on this gasket. However, in talking with Matt Schreck, another engineer here, he said, there's usually only 2. So he actually modified the model, removed 3 of those seals on that. Now we know we need to press this lid on, and we want to keep the press force under 30 newtons, or roughly 6 pounds. Anything more than that would probably be too much for most people to press this on, or it would just be a bad experience. So what I did was I loaded this model into 3D Experience, and then I shared this with Matt Schreck. So Matt is a lot better versed in the nonlinear caveat of the software than I am. So I just simply shared this with him, sent him a message saying, hey, Matt, can you take a look at this model? And I did all of that through 3D Experience. He went ahead, downloaded the model, and what that did then was he was able to set this up. So we're now looking at Matt's screen. So you can see he modified the model to have only 2 seals on that gasket. And he went in and he is going to modify the assembly a little bit. Now, he also cut off the bottom of it. We don't need to access the entire picture, just mainly the upper lid. We want to understand the press of the gasket. He's also starting a FEMREP here, and he's doing this as an axisymmetric. So why analyze the entire model when really that gasket is symmetric 360 degrees? So he's going ahead and he's also assigning a mesh size when this FEMREP generates. So when he selects OK, we can see that that is now cut along that section with the axis, and this is an axisymmetric model. So he's going to go ahead and add in the materials, so the polycarbonate for the lid and the pitcher, and he used a hyperelastic silicone for the gasket itself, or hyperelastic rubber. We now have that model set up as far as the finite element representation. He's now adding a tie between the gasket and the lid. This is an overmolding process, so we're assuming that those two are bonded or tied together. He's now going to go in and start setting up the model. Now, different from what I did previously, this is an explicit dynamic analysis, meaning we're going to actually iterate the movement of this through time. We're also going to understand what is happening along that entire application. He also said that he's taking the top of this lid and he's going to move it vertically 15.25 millimeters. That's the distance to kind of push this down. He's solving this on the cloud, and he's using 8 cores. 8 cores are available through the cloud for free for that solve. And once that solves, we can take a look at those results. And with these results, we can actually step through time. You can see that on the upper right-hand corner of the screen and understand what is happening as this solves. So we're looking at von Mises stress, and we're looking at this as how it is kind of moving down. Now he's going to change the results here a little bit, kind of see a cross section of this. Because it is axisymmetric, we can look at this in a full 360 degrees. He's animating the result, and we can see how the stress develops in the rubber or the silicone seal, and as it's kind of being pressed down along as it drags along that pitcher wall. We can also look at things like contact pressure. Now, one of the things that we're going to see with this is the contact pressure is actually fairly low. That's not what we wanted. We wanted a pretty high contact pressure to hold this in place. We are noting that the lower seal has a higher contact pressure than the upper seal. What we may want to do to kind of even that out is maybe shorten that lower seal a little bit. So that's kind of adding to the contact pressure there, but there's very little contact pressure on the upper one because we're already making a lot of contact with the lower seal, because that pitcher does have a sloped wall. The other thing that we're going to look at here is we're going to get an XY plot, and we're going to look at the force to push this down. Now, unfortunately, the force is a little high. It's 180 newtons, roughly 40 pounds to push this down. So our contact pressure isn't as high as we want it to be, but our force is. And that's probably because of that lower gasket lip being too long and the pitcher kind of angling down. So we need to do a little work on this model to really get that lid straightened out. So we have to revisit the seal design, but we're able to see that up front before we go to prototype this. So this is invaluable information to save us money on cutting that mold. We are able to see that virtually. So let's look at an advanced drop test. So this kind of validated a little bit of that lid issue as well, in how it would be kind of held on. So what we're going to do is we're going to drop the entire pitcher. The handle with that friction fit, we're going to have the lid already pressed on with an interference fit. We have a fluid inside the pitcher itself, and we're going to drop it from a certain height and kind of understand what's going to happen. So Matt did this as well. He said, you know what, let's look at that lid further and see, is it going to hold on as we set up this explicit dynamic analysis to drop this pitcher down. So you can see he's adding the meshes into the model. Pretty refined mesh on the handle, the basket handle itself, on the lid, and on the seal. The pitcher is going to be fairly coarse, not as refined as the rest, but we're going to get a mesh on that here as well. And then he also added a ground object below as well. So we can see he's kind of setting these up. He's going to go through and manipulate the overall mesh size. He's actually doing a hex dominant mesh, something that's very specific to 3D Experience and Abacus, which is actually pretty nice. Now, from there, he generated the mesh. We're going to go ahead and look at adding the materials into the model. So again, he's going to add these into the solid section, so the appropriate polycarbonate for the pitcher, the appropriate polycarbonate for the lid, the silicone for the gasket, and the nylon for the handle itself. So he's adding those all into the model. So we have those materials assigned. From there, we're going to go ahead and set up the boundary conditions. So inside of 3D Experience, what we can see is going to switch over to Structural Mechanics Engineer, and he's going to start adding in things like the initial velocity. He added in the general contact into the model. And this is actually pretty interesting what he's doing here. He's adding something called spherical particle hydrodynamics. So this is called an SPH element. So he's able to take those bodies that represent the fluid inside the pitcher and add to them a way of finite element analysis, treating them as though they are a liquid. So the very cool part about that is when we drop this, we're giving it an initial velocity down. Those particles inside the pitcher are going to behave as though they're a liquid, and it's going to add additional force, additional impact into the design. Now he's running this on the cloud. He's using credits. Credits are consumable, and he's running this with 192 cores of cloud computing power. And we can take a look at the results after that finished running. So we can see here we're back on my screen. So Matt ran the results. He felt that they looked pretty good. He messaged me through 3D Experience and said, hey, Robert, please take a look at the results. Tell me what you think. So what I'm doing is I'm actually pulling those results down from the cloud. So we're accessing those, and I can start looking through them. So we can see when I fast forward to the very end, what a crazy result this actually is. You saw the fluid kind of coming out of the pitcher. You saw the lid fly off, so we don't have enough contact pressures, validating that from this impact result. We can also see the basket flying off of the pitcher as well. We would expect to see that. It's only a friction fit, of gravity effectively. And we see the particles. We can see the fluid leaving the pitcher, which is the really cool part of this analysis. So this is a finite element analysis using an SPH element to represent the fluid, which is really, really cool. So we can see this animation. We can see what that would look like. I am prone to dropping things. This would be all over my kitchen cabinets if we stick with this design. We need to find some way of holding that lid onto the model. Now we can see more than just, hey, we're going to spill the liquid. We can look at things like stress on the pitcher. How does this compare to the maximum stress that the polycarbonate would be able to see, right? Are we going to be cracking the polycarbonate during this drop? What is the stress on the basket itself? Is that within what the nylon can withstand? Kind of understand what the pitcher looks like. The lid itself, we probably would want to expand the ground plane so that the lid would be in contact with it as well. But, first pass on a drop test, but we're kind of getting a good feel for what this would look like. So we can see displacement here being shown as well. So a lot of good value with that drop test. So structurally, we're looking pretty good with respect to the model. We still have to do some rework on the lid itself, but overall, we're looking pretty good structurally. Let's go ahead and look at fluids. Now, the blender has a motor controller board consisting of capacitors, controller chip, heat sink, transformer, and other electrical components. Due to the shape of the blender's base, the feet would need to be inset, causing stability issues. Now I used SOLIDWORKS motion to kind of understand the tipping forces, and with those feet being inset, because it has to look like a cube, it just was going to have some problems. So we switched to an injection molded rubber mat, and that was designed to kind of elevate the pitcher and give it some stability with those tipping concerns. However, most blenders are open on the bottom so that air can move in and out through the bottom of the blender. This is going to block any vents that we will potentially have there. So what we're looking at doing is adding vents to the sides of the blender to kind of understand, is the controller board going to exceed the chip's maximum temperature? That maximum temperature is 85 degrees C, and we need to make sure that we stay within that. Now, we're going to be doing in electronics cooling analysis using CFDs, Fluid Dynamics Engineer, and we really have three areas that we can add vents. So on both sides, we can add vents to the lower section. We can add vents to the upper section of the blender on both sides. This is actually what marketing likes the most. And as an engineer, I kind of feel that we need both the top and the bottom, and we're going to try to prove that out. Now, we're looking at this as though it's steady state, so it's continually running. So imagine, my 11-year-old just holding that button down for 20 minutes for no reason. We want to make sure that we're going to be under that 85 degrees C with respect to this. So I actually used 3D Experience to do this. Now I imported the model from SOLIDWORKS directly into 3D Experience. I'm just opening up the SOLIDWORKS model here. And the reason I'm showing this is I'm actually pretty pleased with how it came in. This is probably one of the best looking models I've seen come in through 3D Experience. We can see our report for that import, and we can actually see all the colors came over with the board assembly here as well. So I'm pretty happy with that. Now, once the model is imported, I can initialize the simulation. So I'm going to start Fluid Dynamics Engineer, and I'm going to start by adding a name to my simulation. I'm creating the fluid model, and I'm also specifying that it is steady state in that step. Now, once that's been imported, I can go through and just make sure all of the bodies that are contributing to the simulation are included. And here I'm basically saying that these are all the parts in the analysis. I'm going to pick my region. I'm going to specify where that is. It is going to be an internal analysis. And then I can actually select my openings. Now I'm showing you the setup on the lower vents only, but we'll look at the results for all three. And here I'm basically specifying my openings. So we can populate automatically the edges of the openings and specify that that is a boundary condition face. Basically, you can see that with the blue disc behind the scenes there. We're going to do the same thing on the opposite side for the vents. So one of the things that we could have done is run a cut through horizontally all of these and pick this all up in one file swoop, but I thought that it would be important to have the discrete openings on this model. So we now have that all set up. The next thing that we're going to do here is we're going to define some of the section properties. So we're going to specify in the model that this domain is going to be air. So we're going to specify that here in the model with those fluid properties. I'm also specifying where we have a fan at the bottom of the motor to cool this board, that is going to be air in and around that area as well. From there, we're going to define our solid section properties. So I have some custom materials in here that are specified as the chip, the heat sink, which is actually going to be in aluminum. We also have the PC board, the capacitors. We're going to add all of those mechanical properties in there along with the materials to the model. Now, once we have those, we can set up the study, and then we can mesh the model as well. So we're going to go ahead and do a mesh review first. So we're going to look at adding some mesh control into the model. Now, there's two meshes because we're doing heat conduction and solids with this. We're going to add mesh control to the fluid domain. So we want to make sure we have good representation of the fluid in and around these solids. And then we're actually going to mesh the solids themselves as well. So here I'm setting up all the mesh controls for the fluid domain. And we can see that model here, and we're actually going to look at a section through the solid mesh, which is a solid geometry, as well as the fluid domain as well. So if I move this, we can see what that fluid domain mesh looks like, and then the solid mesh as well. From there, we're going to set up the boundary conditions of the study. Here is my pressure outlet. So we're just specifying that that is ambient conditions. I'm going to go ahead and go in and add additional boundary conditions here. I'm going to specify, let me hide this, and we're going to add an internal fan. So I have a rough fan curve for what that blade would be producing at the 1200 RPM that it would be spinning, and I'm going to specify my inlet and outlet phase for that. I'm also going to add in my volumetric heat sources. So I'm going to add a certain amount of heat power for the large capacitors, the small capacitors. I'm also going to do that for the chip, the transformer, and all of the other electrical conditions in the model. So I'm also adding in a solid interface because the chip, the transformer, and so forth to the PC board have a certain resistance due to thermal paste or thermal glue. We can add that into the model. All right, so we are set up to run. I'm actually going to run this on the cloud. Now I'm not going to use any credits. I'm going to use the default included number of cores, and with Fluid Dynamics Engineer, that is 16 cores of cloud computing. And these are the results from that. So looking at the model with just the bottom vents, what we can see here is a velocity plot, and we can see the velocity leaving those bottom vents. So we're drawing some of the cooler air from up top, but we really don't have an inlet there. And we actually see that there's a difference in the amount of velocity coming out of each one of those vent openings, and that's because of the shadowing from different components. Certain components are blocking the air from leaving certain vents. Now we can also look at temperature. This was the main concern that we had. And in here, I'm going to move this. We're doing a cut through of the chip, and we can see that it's 93.2 degrees Celsius. We're exceeding our temperature. The lower vents are not going to work. We're also kind of seeing the flow trajectories, and the bulk of the air is mainly at the bottom of this study, kind of holding in that heat. We're not cooling that chip enough. Now let's go ahead and look at the upper vents. So this is the upper vents only. Again, we're looking at velocity. We can kind of do a plot section on this, kind of get a feel for what that velocity looks like in through the fan. We're kind of dead ending the fluid. You can see a high velocity up against the wall, and it's kind of recirculating, but we're not getting any movement there. So not quite what we wanted. Now, if we look at the temperature for this, it's probably going to be better because we're drawing cool air in from the top. We're blowing it down over top of the chip. And we see we're at 88.6, so we're still not exceeding or below the 85 degrees. And we can see a lot more air movement from the top and the bottom with those vents. Now, it's still not quite good enough. Let's look at the full set of vents, the upper and the lower set of vents here. So we're going to switch to that study. We can see we've got a lot of velocity coming in at the top, a lot of velocity going out at the bottom. We're getting a good airflow in this design. We can see that pretty clearly with what that velocity plot looks like. Let's go ahead and move the cross section here and switch to our temperature result. And what we're going to see with this is we're at 84 degrees. So at steady state, no matter how long my kid holds that button down to run this blender, right, we're at 84 degrees. So we're beating or we're exceeding that requirement by 1 degree Celsius. Now, could it be better? Yes, we probably might want to add some vents in the back of the design. Maybe look at reversing the fan, right? Draw the air in from the bottom and push it out through the top. One thing to note, we are not including the heat generated by the electric motor itself. So a couple things that we need to refine with this model, but we're getting there. We're looking pretty good as far as the outputs. So to review, the lower vents were at 93.2 degrees C. The upper vents were at 88.6, and the combination of both is at 84. We probably need to do a little bit better, but we're looking pretty good in our development of cooling these electronics. Now, CFD wouldn't be complete without the mixing analysis. This is a blender, at the end of the day. So we need to make sure that we're going to blend inside the pitcher really well. So we use SOLIDWORKS flow simulation for this. And I'm going to show you the setup on the end pitcher design, at least the design of the pitcher where we are at now, but we will be looking at the comparison between the other rough ideas at the beginning. Now, this was set up inside of SOLIDWORKS flow simulation, and this is a transient analysis. So we are going to be spinning. We're going to be using a sliding mesh to rotate the mixing blade. We're using gravity pulling down in the negative y, and we're using something called free surface. And what that is we have air sitting on top of the smoothie mixture. In this case, I actually use applesauce to represent the fluid in the bottom of the container. Now, a couple things in there. I actually have 2 layers of applesauce in the model, and the reason for that is I have 2 different temperatures of that fluid in the model. So my initial fluid everywhere in the model is air. You're going to see here that I set up some initial conditions for the fluid. Now, first we're going to look at the rotating regions of the model. So again, we're rotating this blade at 1200 RPM to do the mixing, and we have an environmental pressure at the top of this. So we're allowing air to move in and out of the top of the blender. We don't have a lid on this. The initial condition for the applesauce is specifying applesauce on the top layer at 35 degrees Fahrenheit. And at the bottom layer, we're going to specify the same thing, applesauce for that volume, but we're going to have a higher temperature. Now, I did this in 2 different temperatures, 62 degrees and 35 degrees, because I want to see how much or how well these mix. So I'm going to be looking at the average temperature at the end of the study for both of those. I did add a local mesh refinement into the model in and around the blade, and we can take a look at these results. Now, with respect to the results, we can look at cup plots in the model. So let me go ahead and load these results, and we will look at the mesh first. So it's a very uniform mesh through the model. That's something that's pretty important for a sliding mixing type scenario. So that mesh looks pretty good. Let's go ahead and hide that, and we will look at the immiscible fluid in the model. So meaning immiscible applesauce. So this is going to show us at the end of the 0.05 second run, right? Actually, sorry, at this 2 second end of 2 seconds, what the fluid looks like in the model. So kind of understand what that is doing from the surface between the applesauce in the air itself. Now, I did actually run this for 5 seconds total. You'll see those results here coming up, but these results were up to 2 seconds. We can also see the velocity plot on the surface of the applesauce. We can kind of see that really nice mixture rolling in onto itself. This is actually something that I saw in marketing material for other blender manufacturers, and we're actually seeing that same behavior virtually inside of flow simulation. We can also look at the temperature in the temperature profile again. This is 2 seconds of runtime, but we actually ran this for 5 seconds. You'll see those results here coming up. We can also look at a surface plot of the blade to understand the pressure, and then we can also look at an ISO surface to understand what does that surface look like in 3D with velocity presented. And then we can also look at those goals to understand the average temperature at the end of the run. Now let's take a animation cut plot here and just kind of understand what's happening. So this is a square picture to the round at the bottom. What I wanted to show here is just the animation. We are rotating the blade. We're kind of driving that fluid. We're seeing a vortex create or start. Now, one thing to note, the next animations that I'm going to show you are for the 3 different picture designs. One thing to keep in mind is the blade does not look like it's spinning. However, it is rotating at the 1200 RPM. So this is the first picture that we came up with. It is a round top to round bottom. That blade is rotating at 1200 RPM, and we can see it's a very violent vortice in this. And this is running all the way through 5 seconds of run. Now, if we look at this from the isometric view on the right, and then the temperature view on the left. So we can see that there is a difference of 3.2 degrees Fahrenheit from the upper fluid to the lower fluid. We're not quite mixing as well as I wanted to. We still have a pretty decent difference in the in the temperature there. So I'm not too happy with that. So from there, I kind of said, okay, a lot of pitchers that are on the market are a square to round design. We can see that here. Again, a very violent kind of mixing taking place. However, we are kind of seeing a little bit more of those four corners coming together. It just still is quite a bit with that 1200 RPM. And we can see here we had a 3-degree temperature difference between the upper and lower average temperatures. Again, quite not mixing as well as what I wanted to see. So the thought process was, let's slow this down. Let's add some ribs to the pitcher. And that was what you saw the setup on. So we're seeing a little bit more of that happening. It's not quite as violent of a mixing. However, you're seeing a little bit more movement at the upper surface, but not as much down below. We're kind of slowing that fluid down, and you can see from the temperature plot at the end of the 5 seconds, a lot better temperature average difference, and that is 0.16 degrees. So we're 45.79 and 45.94. We're looking really good as far as the mixing is associated with this. One of the things to look forward to in this is maybe we stick with the ribs, and maybe we incorporate those into the square to round pitcher. Maybe we take and we refine the ribs, we optimize the ribs. Maybe they don't poke as far into the pitcher. Maybe they're thinner. Maybe they extend every other halfway from the top to the middle, and maybe from the bottom to the middle every other as well. Different designs of the pitcher, but this allows us to iterate, understand what that pitcher looks like, without even having to create the mold, without having to create the blender, without having to physically test this. So we have unlimited iterations when it comes to the blending, unlimited different design possibilities. We can really get inventive with what that pitcher looks like. So from fluid analysis, let's look at manufacturing analysis. And this is where we start looking at, can these plastic components be created. Now I'm using Plastic Injection Engineer to kind of look at a simple fill analysis on that bottom bearing housing for the motor mount. This really just holds the shaft in place. So it isn't structurally too important, but it is important to make sure that that hole not only fits the bearing, right, the lip fits the bearing, but also holds the shaft perfectly centered. So here I'm adding 2 injection locations, one on either side of the model, and we're injecting this with a certain amount of fill to see, is this going to work? Now we can see the mesh generates pretty quickly. Let's go ahead and take a look at the results. Now with the 2-gate fill, excuse me, it isn't as good of a result as I expected. We're actually seeing that it is an uneven fill. All the corners are not filling exactly the same. You can see that through the fill plot. We're also seeing a good amount of shear in the model here as well. So if I look at the pressure at end of fill, we have a higher pressure on 2 ends versus the others. We can also see the flow front central temperature. We can see the velocity vectors at the end of fill, and we can see the shear stress. And we've got a little bit too much shear stress in this model for comfort. It's not quite a good design. So what we're going to do is we're going to switch. I actually talked to our injection molding engineer, Bill, and he said, you know what, switch to 4 gates. That's what I would recommend in this analysis. So that's what we did. So he actually guided me through this, and we switched to a 4-gate system with a sprue and 4 gates coming directly off of that sprue. Now the nice part about this is, through Bill's advisement, this actually had a lot better benefit. Setup was pretty much the exact same. We have a series of vents, so we did a venting analysis on this as well to kind of make sure that the pressure at end of fill was good. We didn't have any dieseling areas, but what we were able to see here is from the fill, we were able to fill very evenly. So all corners filled almost at the exact same time by switching to a 4-gate analysis. We can also see that the pressure at end of fill was very even. The flow front central temperature was pretty even. The ease of fill was very good, and we can also look at the shear, and the shear is pretty much non-existent in this model. It's very even. That gives us a good feel that this part is not going to warp off of its central axis. So we feel pretty good about that. We also ran a pack analysis, so we held pressure on this to kind of keep the molten material in. And what we can see here is that the residual stress on this looks pretty good as well. Now, I took that one step further, and in SOLIDWORKS Plastics, we certainly could do this in Injection Mold Engineer, but in SOLIDWORKS Plastics, I wanted to show you that we can do a cool and warp analysis here as well. So if I pull up SOLIDWORKS Plastics, we can see that we have a little bit more to this analysis. So it's a fill, pack, cool, and warp. And with this, we have certain settings for the material. So we applied the polymer, so we can pick that out of the database. Same thing as what we did inside of Injection Mold Engineer. These are pretty much the exact same software, just one runs on the platform, one runs right inside of SOLIDWORKS. So we can see the cooling channels were defined in the model. We actually even have a baffle through the center to kind of cool that internal bearing area that typically would be kind of hard to cool otherwise without a baffle. We have the cavity specified, and then we also have a virtual mold to take away heat as well in and around the body. So we can specify that here as well. We're using a sprue with a 4-gate location, so our injection location is at the top of that sprue. We also defined a clamp force in the model in a clamp force direction. And then we have our air vents specified as well. So again, the same venting locations as we used in Plastic Injection Engineer. From there, I have my cooling channels, and these are defined with a specific flow rate and fluid for those and a given temperature. So that's specified for all 5 of those cooling channels, including the one with the baffle. I also ran this using a solid mesh. Now the solid mesh is going to give us a better parameter with respect to the warp analysis. So I can show the solid mesh on the part. We can also see the runner. We can see the cooling channels that are meshed and the mold itself. So all of those aspects are meshed using a solid. Now from there, let's go ahead and take a look at our results. So if we look at the fill analysis, it's going to look very similar to what we had in Injection Mold Engineer. And we can see here, if I animate this, that fill kind of coming down, we can see through the cross section because we did a solid mesh with this one, also available in Plastic Injection Engineer. And what we see is how those flow fronts come together, kind of going down those ribbed sections of the vent and finally fill out those corners. We can stop that animation. We can take a look at the weld lines. Again, that same weld line prediction is what Injection Engineer gave us. We can look at the velocity vectors at end of fill as well. We can look at the pressure at end of fill, pressure at end of packing, the switch time, the shear rate at end of fill, again, low shear rate with the 4 injection locations. We can also look at sink marks, so how much sink might take place in the model. We can also look at the ease of fill, so we can see that this is going to fill pretty evenly and easily. We can also see the gate contribution, so this fills pretty even with those 4 quadrants. Let's go ahead and look at the pack results. So we can see the pressure at end of fill, we can see the temperature at end of pack, we can see the volumetric shrinkage at end of pack. We can also see the frozen areas at end of pack. So it's looking pretty good that this part can be ejected. We can look at the cooling results to understand the temperature in the model. So what temperature are we seeing with the cooling channels? What temperature are we seeing on the part? So this is actually part cooling time. We can measure different areas on the model, kind of understanding the difference between those point locations that we're picking as well. So we'll turn the measure tool off. We look at the cooling temperature, the temperature at end of cool, the mold temperature at end of cooling. We can also take a look at the mold visibility, see what temperature that has. We can also do a section view of the mold to kind of understand the temperature in and around the cavity or the part itself and the cooling channels, which is actually pretty interesting. We can also then look at the cooling channel temperature here as well. So let's go ahead and switch to the pressure of the cooling, and we can see the pressure within those cooling channels through that cross section as well. And then lastly, let's take a look at the warp result. So in here, we can switch and take a look at the deformation scale. So we'll make this 10 times. So increase that to kind of see how is it moving. So we can kind of see it shrinking towards the center. The good news about that is it is kind of keeping the center centered, right? So we would expect that hole at the center of this part to be pretty much concentric with where it should be. Again, this is exaggerated 10 times, and we can see the animation of that kind of shrinking down towards the center and kind of puckering up towards the top. So some of the other things that we can do here is we can see the in-molded residual stress, the quenching thermal stress on the part, the total stress displacement, the sink mark profile, and this is an accurate measurable sink mark. And we can look at the in-molded residual stress and then the demolding von Mises stress as well. We can also export this out as a deformed shape, which is actually pretty cool. So we can put this back into the full model in its deformed value. So we can see that here. If I right click on my result, my warp folder, and choose create body from deformed shape, we can actually do the actual warp or a counter deformed warp if we wanted to. We can save this out to a new part file. And what we're going to get is we're going to get that deformed shape. Now, the nice thing about this is I can put this back into the main model to understand, are my holes going to align properly? Are we going to be able to, is this going to fit the bearing? Is that going to keep that shaft centered? So this is the deformed body exported out of SOLIDWORKS plastics. So lastly, we know our picture can be probably, or we know our injection molded parts can be manufactured pretty easily with the help of injection mold engineer in SOLIDWORKS plastics. Lastly, let's take a look at the electromagnetic simulation. So we wanted to look at the antenna placement. Now I reached out to our resident electrical engineer, Clint Patton, and I talked to him about the Wi-Fi antenna. Told him this device needs to be Wi-Fi capable, and I told him that I probably would want to put the antenna at the top of the design. However, he kind of laughed at me and said, well, I'll tell you where it best is placed using CST Studio for the electromagnetics. Now, he used a program called Antenna Magus to create the antenna. So he was able to actually find a 2.4 gigahertz antenna that would work really well for this model. And he's able to use Antenna Magus to generate this antenna, create it, and create the solid model of it. Now, the cool thing about that is he can actually take that antenna, bring it into CST Studio Suite, and analyze how this antenna is going to generate the far field and near field parameters. So what is this going to look like? And we're going to see that here in a second. Once he gets done setting this up, he's going to start the simulation. And from there, we're going to take a look at the results on the antenna itself. So it's generating those results. And once it finishes running, we can see the result of that. So from there, what we had was the near field and far field antenna. So what we really want this to look like, and Clint explained it as almost an apple. We have two really nice lobes being presented from this antenna. that gives him a good feeling that this is going to work in the model. Now from there, what we did was we did or Clint actually did a analysis on the blender itself. So he's setting up the analysis, he's bringing in the blender, the full blender model, and he's generating this inside of CST Studio. So he's picking up the blender model, bringing in the assembly, and he's going to pick the parts that are critical for what he is doing. So we can pick this up. It's loading that into CST Studio Suite, and he's going to add the additional components in that are needed. So he's going to bring in the controller board. He's going to place that in the model. He's going to bring in the antenna as well. And from there, what he's going to do is he's going to add specific materials into the model. Now he pared this down to the specific areas that are going to affect the antenna. Now, the first one that he's showing you here is with the antenna on the back wall vertical. This is what he recommended, and he's going to show me why, through the use of CST Studio, why my antenna placement was bad, right? So he's going to go ahead and set up the simulation. He's going to run that simulation as well. So he's starting the solve right now. He's going to let that solve through, and we'll take a look at the results of this. Now, with respect to the results, he has the ability to do a lot of different plots. So what he's looking for, or what he's going to be showing here, is how that antenna is radiating or releasing the Wi-Fi signal into the environment. So we're seeing this in a cut plot type manner. Now we can see how the other materials in the model or in the blender are affecting that, and how it is effectively radiating out from that antenna. Now if we look here, we can also see that from a vertical, and we can see that those two bubbles on the top of the antenna and how those radiate and then come together, that is how it propagates the wave out into the environment. And this is actually showing a very good wave propagation to the beginning, or sorry, to the front, the back, and actually all sides of this blender. So Clint's intuition, he's an incredible electrical engineer, was to put this vertical on the back wall. This is truly what the best placement would be. So we're seeing a very good radiation or radiation of the Wi-Fi signal out of this position. We can also see how these solids interact with that signal, how that signal wraps around those solids as well in the study. And if we look at the far field result, we can see how that's actually radiating from the blender itself. Now, Clint said, well, I'll entertain Robert. He's a mechanical engineer. He doesn't know a whole lot about electronics, which is very true. I'll put the antenna at the top of the design and lay it horizontal like what I had mentioned to him. And what we're seeing here is why that's a bad idea. So with the antenna laying horizontal versus vertical, and with it being at the top, we're actually seeing that the signal is only being emitted from the front of the blender, which means if you were trying to connect to this from the back side of the blender, you would have very, very poor signal associated with that. So we're kind of seeing that through the simulation here. So it's all going to the front. That's how it's propagating. The signal through the back is very, very poor. And we actually can see that here in the near field and the far field results. So if we take a look, this is for the antenna at the top. You can see the bulk of that near field antenna propagation was to the front of that model. Here, this is with the antenna on the back looking at the near field, and it's a nice bubble in and around. Again, the horizontal top antenna is all to the front of the blender, where previously with it vertical, it's wrapping around the blender itself. So this is a lot better propagation for the antenna signal, and Clint kind of proved that very quickly to me using CST Studio Suite. We can also see here that the antenna in the vertical position, it radiates at the 2.4 gigahertz. You can see the red line is the vertical position, the green is the horizontal position. that is not actually sending the signal at 2.4 gigahertz. It's actually sending it a lot higher just because of the orientation of that signal. We can also see here in the far field, the red, which is the vertical antenna, that has a nice circular band of signal, uniform band of signal leaving it. The green is the antenna in the horizontal position, is all towards the front of the blender. So Clint was able to prove out where he wanted the antenna, pick the antenna, and we feel good about going forward and saying that this is going to be a Wi-Fi capable component, and you're going to have service no matter where you're at in relation to the blender. So that was a look at the design process so far. We saw that we still have some design left to do in this blender. The seal for the lid, maybe the vent locations for the electronics cooling, and maybe optimizing what that picture looks like from a standpoint of mixing. So thank you very much for attending the webinar. You can contact me at rwarren@goengineer.com. And I wanted to give a special thanks to Bill Roos, Matt Schrack, Clint Patton, and Alex Worsfold for helping put this presentation together. Thank you very much.